Welcome back. So the question here is, we know how to go from the electric field to the electric potential. Can we go backwards? And we certainly can. In fact, if we're going from field to potential, we integrate it. Sure enough, if we want to go the other way, from potential to field, we're going to need to take a derivative. The particular derivative that we want to take is the negative gradient. If you've taken multivariable calculus already, you're probably a little bit familiar with the gradient, but it may have been a little bit since you learned about the gradients. We'll talk a little bit about what that is. So the gradient is basically the derivative in the steepest direction. We're kind of used to dealing with one-dimensional functions a lot in physics, but suddenly we have functions of 3 variables. And so if I say take the derivative of v, you might not know what to take the derivative with respect to. So the gradient is telling you what specifically to think about. It's the derivative in the steepest direction. If you remember your kind of multivariable calculus course, one way to write that is as the derivative of v in the x direction, or sorry, with respect to x in the x direction, and then the derivative of v with respect to y in the y direction, and you can keep going with additional directions if you have them. That's kind of a way of symbolizing the gradient. I like to think about it a little more conceptually as this steepest derivative that you're going to get. You can think about the component of the electric field, the kind of dv dx, as being the derivative of v in that direction. I want to show you what this looks like in our graph. So I will show you our equipotential graph that we had a couple of videos ago. And I'm just going to pick kind of a random point here, maybe this one up here. And I'm going to try to find the gradient just by kind of looking at the picture graphically. I know in general that derivatives are slopes, but it's kind of tricky to see where there might be a slope showing up on this. So I want to think really carefully about what this means. Again, this is the equipotential graph for a positive point charge. I got a positive point charge maybe hanging out in the middle here. And I'm sitting over here and I want to know what's the biggest value of the derivative that I'm going to be able to get. And one thing that I'm going to kind of imagine is that I'm kind of standing at this point. I could almost imagine it as being on the side of a hill. There's a little hill slope. And what you'll see is that I can take the derivative in a lot of different directions, right? I could take it that way. I should get a different tool for this. I could take it that way. I could take it this way, right? Any of these directions would be perfectly valid ones for me to take the derivative in. I want the one, the direction that is the biggest derivative. And the way that I'm going to think about that is I'm going to try to understand how to read a derivative on this graph. And to do that, I'm going to think about what a derivative actually is. So a derivative, if I were to kind of just think about a simple example, right? dv dx, for example, right? Well, what this really is saying is take a small change of v, delta v, and divide it by a small change of x. And if I'm doing a multivariable derivative, I want to be careful to hold the other, the variables in the other directions constant. So if I'm in the x direction, I'm going to hold y constant. I'm going to move in the x direction, right? So basically, this is a ratio, right? I want to know how much does the potential change, how much does space change, delta x, and then divide those two things. Well, I'm going to look at a couple of those on my little picture here. So I could try the x direction out here, right? And that would say, start here and then go a little bit in the x direction. And there I've hit a line where I've got another value of v. And I could calculate what delta v is there. If I just use my numbers from the first video, I think I had a difference of 1 volt between those two lines. And then I would need to measure the, so I'll go ahead and put 1 volt here. And then I need to measure the distance here, right? So I need to figure out how far is it from this line to that line. And maybe that's, I don't know, 0.2 meters. I'm just making up a number for that right now. And that would give me the value of the derivative there. But I can do that in the y direction too, right? I could instead say, what is that thing? And what you'll notice is delta v is the same between those two adjacent lines, right? Everywhere on the first line that I started with has the same value. Everywhere on the second line that I'm ending on has the same value. The delta v hasn't changed, but delta y, the change in position in the vertical direction, might be different than delta x. In fact, just kind of eyeballing it here, it looks kind of like delta y is a little bit smaller than delta x, which would mean that the denominator, if I find this for delta y, is smaller, and the value of the derivative is then larger. So I found two derivatives here, one larger than the other. If I want the value of the derivative that is the largest, then what I really want to look for is what is going to make that denominator the smallest. And to get that, what I really want to do is look and see how close is the nearest line. And so what I do is I kind of look and see which direction should I move from the point I'm starting at that gets me to the next voltage line, the next equipotential line in the smallest distance. And you will always universally find that that smallest direction, that smallest distance direction is the direction that is perpendicular to the equipotential lines that we've drawn. So what you'll find here, and I'll maybe do a quick re-sketch here, is that if I'm at this point, the biggest value of the derivative is going to point that way, right? Perpendicular to this path. But if I'm down here, it's going to point that way, again, perpendicular. If I'm way out here, it's going to point this way, perpendicular. Now, you might have a couple of questions. One question you might have is, how did I know which perpendicular direction to pick? Because it could have been back this way instead. That is where that negative sign in the definition of the electric field came in, right? If you remember back to our other slide, the electric field was the negative gradient, which means that it essentially points downhill from the higher value of the potential to the lower value. So if this is a positive point charge, the potential is really high near the origin, and as I get farther away, it goes down. That electric field points downhill. You can almost think of it as pushing down the hill. Now, the other question that you might have is, how do I know how big to make the electric field arrows? And the way you can tell that is, if this is your kind of process for thinking about the derivative, a change in voltage divided by a change in position, the equipotential map has built into it the feature that the potential is equal, the potential difference rather is equal between adjacent lines, which means that the thing that matters is how close are those lines together. The closer the lines, the bigger the gradient, which means the bigger the electric field. So I'm going to get a really big electric field if I'm in here where the lines are really close together. On the other hand, if I'm out here where the lines are really far apart, I'm going to get a small electric field, which should agree with what we already know about the electric field of a point charge. If I'm really close to this point charge in here, then I'm going to get a really large electric field. The lines, the equipotential lines are going to be close together. If I'm really far away, they're going to be spaced out. All right, that is how we can go back and forth between electric fields and electric potentials. We've covered both directions in class this week. We'll see if we can try this out in a couple of different situations.